Hey there! We're going to go over in this video the limit definition of the definite integral. Some people know this as the formal definition of the definite integral. If you are in a very difficult college course or an AB or BC calculus, you will be exposed to this. You won't be asked to necessarily evaluate it, but you're going to be asked to be able to understand what it's about. So let's do this and let's make it simple. The first question that we should start with is, how can we approach the exact area using rectangles? So if you've watched my previous videos, we've gone over how we can estimate the area between this curve and the x-axis between two values a and b. But we've estimated it. How do we get the exact area? How many rectangles will we need? Well, if you cut up the rectangles into really, really tiny parts, so imagine like taking lots of really tiny rectangles, like super tiny like that. Right? You'd have to cut them up into many, many, many parts. But you see that as you cut up really tiny, I know it's a squiggly rectangle, really tiny rectangles, you start filling up the area more accurately. Okay, so let's think about this in terms of what we talked about with delta x, in terms of rectangles, their heights, their bases, and let's make this really, really simple to start. So we know that delta x overall, when we have a rectangle that goes in this curve, looks something like this. So you'd have delta x is the base of that rectangle, and the height of the rectangle we know is f of whatever the x value is. We'll call it x sub k. So if you've got some rectangle at like x equals 2, the height of that rectangle is f of 2. So we'll call it x sub k for all the rectangles. Now, how do we get the exact area? We would need infinitely many tiny rectangles. Well, if we wanted infinitely many tiny rectangles like this, we would need to, because we have a finite area, right? The area is only so wide, we'd have to slice this area up into really, really thin rectangles. So another way of saying that is delta x would go to 0, right? It definitely would get really, 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 really narrow. Or another way of saying we need infinitely many rectangles, because as n, the number of rectangles, goes to infinity, you'd get some constant b minus a, in this case that's 4 minus 0, all over infinity, so that goes to 0. All right, so overall, we know that we need a limit as n goes to infinity. The number of rectangles has to go there. That's what we've established so far. Next, let's talk about this thing. This means add up a whole bunch of stuff, right? It means have k, right? The values in here go up by ones. And as we go up by 1 each time, we're going to add up everything that we get out of there. Okay, so let's dive into this with this sigma. That's what this is called, sigma notation. Well, again, it means add up lots of things. Heights of the rectangles would be f of x times widths. So add up lots of areas. All right, that's where we're starting. Now let's build on this a little bit. So we know we're going to have to add things up. But the question is, what does this need to be? Because when you use sigma notation, and I'm going to start this thing at 1. You could start it really at any number. Typically it's started at 1 or at 0. What's going to happen here is, just to kind of go over this, if you started at 1 and you go to any number, n, you've got f of x sub k times delta x, and then what happens is you plug in 1. So you get f of x sub 1 times delta x. That gives you the area of one rectangle. Plus, in a sigma notation, you then plug in the next number. It would be f of x sub 2 times delta x. That would be the area of the second rectangle, this tiny little thing here. Plus f of x sub 3 times delta x. And it would keep going on and on and on like that. You keep adding up areas of rectangles. So what we need is, we need some kind of pattern that's going to give us the proper x values to fill in this area perfectly. So what is that all about? So what I'm going to now do is I'm going to draw a bigger rectangle in here so that we can see this. So we've established we need infinite rectangles. Let me get rid of all of that. And what we're going to do is let's draw in a relatively decent sized rectangle, something like this, up like that. And I realize it looks like an overestimate, but at this point we're drawing in rectangles, and I'll use right-hand rectangles, just like that, and so on and so forth. Okay, let's take a look at each of these rectangles as they cover up this area. This rectangle right here would be f of, and let's call that x sub 1. Right, that would be your first x value. So the first rectangle would be f of x sub 1 times delta x. That gives you the area of that rectangle. From there, we now need the area of this rectangle. Well, the question is, how do we get to x sub 2? How did we get there? Well, let's look a little bit bigger here. So I'm going to blow up these rectangles just a little bit so that we can understand what's going on here. So what I'm doing here, y'all, is I am basically putting a microscope to these first 4 rectangles. And if you look at this, in terms of the widths, each of these widths of the rectangles or the bases are all delta x. Oh, okay. Well, so this is your starting value right here, a. Right, that's your starting value in all of this. What's this x value? How did we get there? We took a and we added delta x. We added 1 delta x. How did we get to this x value? We took a and we added 2 delta x's. Oh, how did we get to this x value, which gets us the y value here? We took a and we added 3 delta x's. And then here we took a and we added 4 delta x. So in general, if you've got this rectangle out here, and you want to know, how do I get to that x value that's going to get me my height, f of something? How do I get that x value? Well, you take a, where you start, and you add on to there k number of delta x's. That k would be the number of times that you've added those widths. Oh, that's your x sub k. Okay, so we're starting to build this. So you got sigma. You're going to add up all these areas. This is going to be a plus k delta x. Got it. So we'll start at k equals 1, we'll go to n, and then we'll get f of a plus k delta x. Oh, and then our width is going to be delta x. That again is the height of the rectangle times the width. Not so bad. And so that'll give us the area of any rectangle. And when we plug in 1, we'll get, well, this first one here, a plus delta x. Then the next height, a plus 2 delta x, a plus 3 delta x, always multiplying by delta x to get us the area. And we're adding them up. Now, we've got to be a little bit more specific here. So we'll go a little bit further and we'll have ourselves the integral. But this is what I want you to remember. If you know this, you're in good shape. Now, from here, I've got f of, it's always going to be a, plus, you've got that k. But the question is, what's delta x? Delta x is b minus a over n. So it's always going to be the end point there, b minus a over n, like that. That's your delta x, just plugging it in. Remember, we're starting at k equals 1, going to n, and then delta x again is b minus a over n. And that's it. If you can remember this and this, we can always build here. Now there's one big piece we've got to add on there. I'm going to put it in blue. We need n to go to infinity. We need infinitely many rectangles. So that'd be the limit as n goes to infinity. This right here, I'll circle it, put that in quote marks, circle. That right there is the limit definition of the definite integral. It will find you the exact area. Why again? One last time. What you're doing is, and I'll put the limit here too, you're saying as the number of rectangles goes to infinity, delta x goes to 0 because you have a constant over a large number. So delta x is going to 0 while the number of rectangles is going to infinity, but that will fill up this space perfectly. You'll end up with really, really tiny rectangles and infinitely many of them. The rectangles will each have heights determined by this. It's easier to think of it this way. Your starting value plus however many delta x's you went over will get you any of these heights. And so we'll go up by 1, 2, 3, 4, just like sigma notation does. And you're going to multiply by delta x by each of those heights to get the area of each rectangle and add them all up. And that gets you the true area. Isn't that crazy? I think that's really, really cool. All right, so we're going to do some more with this. It's going to be a pretty lengthy video, this one. Let's keep rocking and rolling, but I think it's important that we're continuous with it. So overall, what we just discovered is the definite integral. The definite integral is this. We saw this in the last bit. And that will give you this symbol. This symbol is shorthand notation for this. Essentially, as delta x goes to 0, that'll happen as n goes to infinity, it becomes dx, a very, very, very small change in x. F of x is still the height of each rectangle. So this is still the height of a rectangle, and this is still the base of a rectangle. When you multiply them, you get the area of a rectangle. That stretched out s we've been seeing for a long time literally means find the sum, add up infinitely many of these rectangles with heights and bases from A to B. So literally, you've got a picture like that from A to B, and we just add up all of these rectangles like this, where each rectangle has a width, now no longer of delta x, but a width of dx, and a height of whatever the x value is at each point. And this is the shorthand for saying add up all those rectangles until we fill up the area. Isn't that beautiful? So that means the area between the curve and the x-axis from A to B, but it's a little bit more than that. So rather than write this out every time, we can write that out. And that, again, stretched out s means the sum. All right, that's cool. That is so darn cool. All right, so we're going to now do one of the harder types of problems in this, which is go from here to summation notation. Again, many of you won't be expected to know how to do this, but if you're an AB or BC Calc, you will. Remember that this is the height. This is f of x. That's the height of each rectangle. And this right here is essentially delta x as it goes to 0. So what I always ask students to do is start out with an understanding or even a memorization of your overall summation integral. You could start at a k equals 0 or k equals 1. I like to start it out at 1. That's just a difference of a right-hand or a left-hand rectangle, like we did in Riemann sums. Because you're getting infinitely many of them, you're going to fill up the exact area. So we have f of a, that's the lower value, and that's to b, plus k number of delta x's times delta x. Remember off to the side here that delta x is equal to b minus a over n. So let's calculate delta x. It'll make the world much easier. So delta x, maybe not the whole world, but you know, these problems. Delta x would be b minus a. It's the overall, that divided by n. So that would be 3 minus 1 over n. The overall width is 2, divided by the number of rectangles, n. So we have infinitely many rectangles, obviously. This is going to go to dx, but delta x is 2 over n. So let's write it out. We've got the limit as n goes to infinity of sigma from k equals 1 to n of f of a is 1, right? You've got that defined here. We've got a is 1 plus k times delta x is 2 over n. So we'll write that as k times 2 over n. There's your 2 over n, 2k over n. And that's the same value we're going to put here, except without a k because it's just times delta x. F of x times delta x. That again is the delta x dx is right here. F of x is right here. All we have to do now is just make sure that we plug this into the function, which is x squared. So the limit as n goes to infinity of sigma k equals 1 to n. F of anything means plug it into the function. We're going to square that. So that's 1 plus 2k all over n squared times 2 over n. That is equal to the integral from 1 to 3 of x squared dx. You might be like, where's the 3? It's in here, right? Delta x was 3 minus 1. It's the span of 2 starting at 1. So overall, what this thing looks like, just as a rough sketch, you've got a graph going up like this. So let's say this is A and that's B. We're filling in the area from here to here. That's it. So you've now found the area from there to there, the exact area with infinitely many rectangles, all of which having really, really tiny widths. It's awesome. Absolutely awesome. Now, let's go on to the next and final type of problem, which is going backwards. How do we write the definite integral from sigma notation into something like this? So our goal is we want a to b, the integral from a to b, the definite integral from a to b, of f of some x dx. So here's the good news. All we need to locate are what are our b and a values as well as what f of x is. Well, take a look at this. Remember that overall, we've got the limit as n goes to infinity from k equals 1 to k equals n, like so. And overall, that's f of your starting value plus k delta x all over n, or k, or delta x over n times k. Sorry, I put that as delta x over n. I'm combining two things there. Let's just write it as k delta x. I think that'll be easier. Let's do it like that. Times delta x. That's it. So remember also that delta x equals b minus a over n. All right, why is that important? Well, we can find b and a just from this. So here, this part right here is delta x, right? We've got the delta x times k going on. So delta x is 4 over n. You see that here as well. Why is that important? Your a value is right here. So you have a plus k times delta x. And so a is 3. We know that. We're just building our problem. I guess I'll put it right underneath here. a is going to be equal to 3. Delta x, well, we know that delta x, the whole thing, is all of this. But b minus a is 4, right? That's in the spot for b minus a. If b minus a is 4, and a is very simple, right, is equal to 3, then b has to equal to 7, right? If the overall width is 4 and we start at 3, then we're going to end at 7. Nice. So now all we have to do, we know we're going to have dx, is figure out what f of x is. Well, let's look at this whole thing. We're taking a number. This number represents all of this, and we're squaring it. So I know I've got x squared from that. We're subtracting 5 times what we're plugging in. So that's minus 5 times what we're plugging in. And so that is equal to f of x. And that's the function we're taking the definite integral of. It's not an easy problem at first when you're looking at it, but it's something that can certainly be broken down. Remember, the key in all of this is understanding this. Heights of rectangles times widths. It was a long video, but one that I hope was very worth your while if you're studying this in class. I'll have many more exercises of this at the end of this lesson. Peace.